Our team will be presenting our case study on the site remediation of the land that covers the current Sydney Olympic Park. Each team member will present their research as follows. I'll be discussing the project background and making conclusions of the efforts of the site remediation. Kustiani will be discussing the site characterization and risk assessment. Liam will speak about the recommended site remediation strategies. Vatsala will highlight the costs associated with the site remediation, and Kushik will discuss the actual site remediation technique that will be used. The location of our site is in the area formerly called Homebush Bay. The environment in the area had been significantly affected by contamination from industrial activities, such as from the state's brickworks, chemical factories manufacturing products such as pesticides, and was also used as an asbestos disposal site. All these activities contributed in some way to the site's contamination. Our team has created a remediation plan to find the cost associated with decontaminating the site and the preferred remediation technique, which will be discussed by the other speakers.
The first step to the remediation of a potentially contaminated site is to determine A, if it's contaminated, and B, if so, by what and how. To find out these answers, we need to perform a few background checks, also known as site characterization. Geology and hydrogeology are two important components. The figure on the left is a geological map of the area. The areas in green are ashfield shale of the Waianamadda group. The light-coloured areas consist of man-made fill and silty to peaty quartz sand, silt and clay. This means that the soil in the area has low permeability, which will have implications on remediation methods discussed later. The figure on the right shows the topography of Sydney Olympic Park. You can see low areas highlighted in blue. Groundwater is likely to flow towards these areas, which are made up of major waterways and wetlands, also adding to the complexity of remediation methods. Another critical aspect of site characterization is to explore the site's history. Next slide. Here you can see a collection of photographs. Starting in the bottom right is an image of the armaments depot, which was used from 1987 until 1997 by the Commonwealth Department of Defence. In 1910, the state brickworks began production. The brick bit can be seen top left and factory bottom left. In 1915, the state abattoirs opened, an image of the admin building shown in the middle bottom photograph, both operating until the late 80s, early 90s. The land was also used as Sydney's rubbish dump, and in the 30s and 40s, numerous chemical factories operated, including the manufacturing of oils, paints, resins, and pesticides. Some of the extent of the pollution can be seen in the bay, image top right, and the poor water quality. It is evident that from years of industrial activity, the site has numerous sources of contamination. Next slide. The contaminants found include chemical waste, petroleum waste, asbestos, industrial hydrocarbons, domestic garbage, and dredging material, among others. Once the preliminary assessment has been conducted, the exploratory and detailed site investigation can begin. Next slide. In 1991, a study of site was conducted in which boreholes were drilled in a 50-metre grid to an average depth of 1.6 metres. A screening criteria, shown here, was implemented to separate areas of high risk to human and ecological receptors and those that were negligible. Essentially, the overall risk was determined, and if it was moderate or high, was decided if the habitat was worth saving for the desired land use. If yes, then the cost and risk analysis was conducted, and if no, an alternative was explored, and so the cycle continues. Next slide. This leads on to the next stage of site remediation, which is risk assessment. This establishes a residual risk by reviewing the significance of impacts to environment and individuals and the ability to manage these risks. A risk matrix is used to establish risk rating of hazards so that the necessary control can be assigned with a suitable level of importance, as seen here. Using the matrix, we have made an assessment of hazards table for Sydney Olympic Park. Next slide. A selection of risks has been presented here. It's been broken up into areas of site in no particular order. Looking at chemical factories, the hazards identified were persistent organic pollutants contamination, as well as scheduled chemical waste contamination. The risk rating before any level of remediation was classified as extreme in both cases due to the range of health consequences, including increased risk of cancer as well as birth defects, as well as environmental impacts, including thermal pollution and eutrophication. The likelihood of these contaminations occurring was deemed to happen most of the time, and thus an extreme rating was given, highlighted in red. This same process was done for asbestos and leachate contamination, as well as acid sulfate soils. Particularly in the case of leachate, a number of chemicals are present, including ammonia, nitrogen, heavy metals, and polyaromatic hydrocarbons, all of which have a significant impact to humans and environment. My teammates will present the remediation methods suggested, as well as actual techniques adopted. However, summarizing quickly, looking to the right of the table, a list of current controls is presented. Continual monitoring and sampling is a vital control across the board. A second risk rating is then given, all of which show the risk has been mitigated or reduced. Thank you.
I'll be talking about remediation techniques that our team has recommended, as well as providing a recommended site remediation plan. The first remediation technique was soil vapor extraction, also known as SVE. This technique involves the use of vacuum extraction wells to create a negative pressure gradient, which in then turn moves the contaminated soil vapor towards these wells. The vapor is then treated and can be either dispersed into the atmosphere or re-injected into the soil. Next slide, please. The second technique, soil washing, involves the removal and scrubbing of contaminated soil. This treated soil is then put back into the site. This usually only occurs in small areas due to its high cost. Next slide, please. The last technique was soil flushing, involving pushing liquid through wells into the soil and removing contaminants through other wells. Next slide, please. This is our recommended site remediation plan. The areas denoted red are soil flushing, purple, soil washing, and blue SVE. Soil flushing is used in these areas because the soil material is clay and silt. We also didn't think it necessary to lower the ground level water table in these areas. Soil washing is used in areas where heavy metal is present, and SVE is used in all other areas. Thank you.
Thanks, Liam. I'll be talking about the costs associated with this project. The site remediation for this project includes activities such as environmental impact assessment, choosing appropriate remediation technique, labor, etc. The costing estimates uses the data from Caudal Commercial Building Cost Guide 2020, and therefore assumptions have been made with respect to the number of personnel required. The cost estimate includes resources needed, such as labor, equipment, remediation technique, and contingency costs to approximate a budget that can be used for conceptual design stage of this project. It should be noted that while the costing has been estimated with great degree of detail, it should not be taken as final budget and needs to be updated during the detailed design and procurement stages of the project. Considering the intrinsic case by remediation technology, the budget has been broken down to number 1, phase 1 environmental impact assessment, number 2, bioremediation technology, number 3, remedial design, number 4, management plan costs, number 5, labor costs, and contingency costs. It has been assumed that the project continues for a period of 11 years on 400 hectares of land with almost 9 million cubic meters of polluted land. This slide shows the cost breakdown associated with this project. For site preliminaries, it's around $8 million. For equipment, it's $52 million. For labor, it's $18 million. For 25% contingency plan, it's around $19 million. And therefore, the total cost is almost similar to $100 million. Thank you.
Now we'll move on to the actual site remediation plan. In 1991, a detailed study was conducted on the soil, groundwater, and stormwater patterns. Based on this study, the initial technique that was adopted was strip and contain, which means the top layer of the contaminated site was stripped off and contained in large pits, while the remaining part of the site are installed with barriers, caps, and gas control systems. This technique was later abandoned because a threat was found to a certain frog species. So, as an alternate, move and contain was a technique that was adopted later, which means the contaminants were moved from one place to the another and contained in the other place. So, movement of the contaminants did not create a problem because most of the land was owned by the government and no additional permissions were necessary to move to facilitate this movement. And bioremediation using microorganisms was used to disintegrate petroleum products. Next slide, please. So now we'll discuss the effectiveness of the technique. This has certain advantages and disadvantages. Some of the advantages includes the minimum health risks, reliability, satisfactory regulatory approvals, and the time frame to install is short. And most importantly, this technique has the ability to handle vapor risks. Some of the disadvantages that are mentioned here are a strict maintenance schedule was necessary, environmental management plan is essential, and continuous monitoring of gas buildup was also required, and maintenance of landfill gas management systems was required, which added to the maintenance costs. Thank you.
Based on our research, it has been found that through remediation works completed in the last couple of decades, substantial sources of contamination have been removed from the site, which has had many benefits, such as increased biodiversity. The remediation technique selected was appropriate for a large site such as ours, and this allowed for any works to be completed safely and to a high standard.